talk about right now is electric fields. So this concept of a field is one we've seen before, and it's very important in physics. And it is the explanation for something that bothered no one less than Newton. Newton himself, when he came up with universal gravity, did wonder, how does the Earth know the sun is out there? In other words, how does this force operate across a distance? I mean, if two things are in contact, you can sort of, understand, although those forces are also felt through fields, you can sort of understand that they're in contact, so one knows that the other one's there. But this action at a distance, as he called it, really, the explanation wouldn't come for several hundred years after Newton, with this concept of the field, which was fully developed in the late 1800s. So what you see here pictured would be an example of, say, the Earth's gravitational field, with thinking of the Earth as the blue dot in the middle here. And then how do things know how to fall, which way to fall, what the strength of gravity is. And that's represented by these arrows, right? So if you're close to the surface of the Earth, you have these rather long red arrows, which are pointed towards the center, or they should be pointed towards the center of the circle here. And they're long, so that represents, the 9.8 newtons per kilogram that we know Earth's gravity is at the surface. Then if you go up a few miles, right, that value is going to get a little bit smaller, but still be pointed directly towards the center. And then even higher, the gravitational force is getting smaller and smaller, therefore. And that, why is the gravitational force on a mass up here smaller? It's not because it does a quick 1 over r squared calculation, gm1 m2 over r squared, but rather it just is sitting in a field that is weaker, right? So instead of thinking about gravity as operating through an instantaneous calculation of g m1 m2 over r squared, the modern way is to think, well, the Earth is here, right? That's the m1 in the equation, and it is setting up a gravitational field, which we use as little g, right? We use that equation to calculate the weight. And the second mass is actually sitting in the field and is responding to the field at its location, right? So the second mass doesn't have to know how far away he is from the first mass, or what the actual value for that mass is that is responding to the field locally, right? And that's the modern way of thinking about one of our original physics equations, right? The force due to gravity. This is one of the very first ones up there with F equals ma. We said of all the forces, the force due to gravity is the simplest one. It's m times little g, where little g is the strength of the gravity of the planet you're on. And then eventually we realize that there's a formula for that little g, and it depends on r squared and all that kind of stuff, that it comes from universal gravity. But as a conceptual framework, right, this little g is actually representing these little arrows here. So it is a vector. It does have direction and magnitude. So we've kind of talked a little bit about that with gravity, but it was kind of just more philosophical and a one-off, and it turns out to be super important when you talk about electricity, and even more important when you talk about magnetism. You basically can't understand magnetism without understanding fields. Electricity also gets super complicated if you don't think about fields. So we're going to set up electric fields in the same way, by analogy with gravity, as we did before. Just like Coulomb's law looks like universal gravity from Newton. The force of an electric field, force from electricity, is you're putting a second charge, that's the little q here, inside of a field that's represented by the capital E here. The electric field that has been set up already by other charges that already exist in the room, right? So just like over here in gravity, we think of the little mass as responding to the gravitational field that it's in, and that's where the force comes from. Now we're thinking about the charge is sitting in an electric field, and it's responding to that. So here's what the equations look like, right? If you take universal gravity and divide out the second m, right? This is what we did a long time ago to find the formula for little g. That's how we calculate 9.8 at the surface of the Earth. We put the mass of the Earth here, and we put the radius of the Earth in here and square it, and that's where we get 9.8. And now you can do that for any r value or any m value and find little g for any distance from any mass. And so this becomes a universal formula for the gravitational field. It's not a force because it doesn't have units of newtons, but it's the gravitational field. So we can do the same thing for electricity, because we already know what Coulomb's law is. Divide out the second q, right, and you get a formula that looks very similar, except instead of g, you've got k, and instead of m, you've got q, and now you have the electric field that is due to a charge. Okay? So far the analogy is working pretty well for us, but of course, Oh yeah, let's do one other thing. So looking at these, what would be the proper units for the electric field, right? Just like gravitational field cannot have units of newtons, electric field is also not a force, right? And if you look at the structure here, you'll see you have a force on the top and charge on the bottom. So this, just like little g, originally 9.8 was newtons per kilogram. The electric field will be, which of these? Letter B, newtons per coulomb. So just using the equation, we can do some calculations, right? So if we have a single electron in the room and there are no other choices, no other charges, then that single electron will set up its own electric field in the space around it, just like the Earth does. In fact, it would, the picture would look very similar to this. Just think about replacing this blue dot with the mass of the Earth, creating a gravitational field. Think about it as being the charge of an electron in here, creating an electric field around it. So using our equations, we can actually calculate that value, right? Because we know what the charge is on a single electron, and I'm giving you the R value here, 3 meters away. So if you want to, you could pause right now and do a quick calculation and check your answer. Here's the solution, KQ over R squared, right? This is Coulomb's law without the second Q in there, because that's how we determine the electric field. We divide out that second Q. And plug in all the values, I get negative 1.6 times 10 to the minus 10th. There's our units, newtons per coulomb. The minus sign is telling you something about direction, right? So since if you have a negative charge as your source charge, you're going to get a negative sign. And if you have a positive charge as the source for the electric field, you'll get a positive sign. What do these signs mean? Negative means that the electric field is pointing towards the source charge, and a plus would mean that it's moving away from the source charge. So if you look back at this picture, right, that would be correct to have a negative sign in front of here, right, to indicate that it's a negative charge in the middle, setting up electric fields that are pointing towards it. Right, so the problem with electric fields, or not the problem, but the complication is that electric fields can be sourced by two different things, right? Gravitational fields is easy. All mass attracts all other masses. You don't have positive and negative masses. But in electricity, as we know, there are two flavors of charge, right? So your source charge could be positive or negative. So on the right here, you see a picture that looks like the Earth's gravity field for negative charge. This is what what electrons or any negative charge does. They set up electric fields that are pointed towards it by convention, right? And positive charges, to indicate that they are different, right? Although the strength, if the charge is the same, then the strength will be the same. The direction will be opposite, right? And that's telling you something, right? They do have opposite effects, right? If you were to drop a positive charge in the room on the right, that positive charge would be attracted to the negative charge in the middle. And so it will experience a force that is directed towards the center. On the other hand, if you drop a positive charge in the room on the left here, in an electric field that's sourced by another positive charge, that positive charge will be repelled by it and will feel a force that is directed away from it, right? So the electric field lines are telling you the direction that positive charges will feel a force in the direction of the electric field. So, I mean, it doesn't make sense in a certain way, because charges in motion and the charges that get moved around and all that other kind of stuff is almost always negative charges, right? But at least we are consistent in physics, right? And engineering. Everybody does this in terms of positive charges. Electricity is set up thinking about positive charges being the one in motion. Even when we're thinking about current and wires, and if you're an electrician wiring up a house, all of that stuff is defined in terms of the direction of positive charges. So even though that is the exact opposite, thank you, Benjamin Franklin, from reality, that's what we do. So here are some rules if you want to draw electric field lines, right? Unlike gravity almost always, right, the significant gravitational forces comes from planets and stars, and they're spherical, and so you almost always just get gravitational fields that look like this picture on the right. But for charges, of course, charges, an everyday, we did the calculations before, an everyday charged object might have billions and billions of extra electrons, or billions and billions of electrons missing to give it a net positive charge. And those charges can be distributed all over the place, right? You can get all kinds of geometries is what I'm getting at. And so it is useful to have some mechanisms by which you can draw electric field line pictures without actually having to do calculations, right? So here are some rules that emerge from if you do the calculations carefully and think them through. The first thing is that all the lines that you draw that represent the electric field lines, that's the black lines in these pictures with arrows, they're going to be sourced, if you will, on positive charges, and they will end on negative charges, right? If there are no negative charges, then they'll go out to the edge of the picture, right, in search of a negative charge. And those would be called the sinks, right? So you think about positive charges as being sources and negative charges as being sinks, S-I-N-K-S, right? So that's the language that people use. They can't cross. The reason why they can't cross is because if you do Coulomb's law at any one point in space, there's only one direction for a net force. And you divide out the second charge, and that gives you one direction for the net electric field. If you were to have electric field lines that cross, that would mean that if you dropped a charge right where they crossed, you would have a net force in two different directions, and that doesn't make sense, right? There's only one direction for a net force. The magnitude, when you do a vector diagram like this, a whole bunch of little arrows, you can indicate the strength of the field by the length of the arrow, like we traditionally do with vectors anyway. But the problem with this kind of picture is it doesn't give you the full impression of the field, right? Because it's not filling the space or anything. So the standard thing is to actually draw pictures more like this, where you have continuous arrows indicating that the fields are filling the entire space around the charge, right? And so the way you encode the strength of the electric field is actually in the spacing of the lines. You see, as you get close to this negative charge, the field lines, the black arrows, are very close together. They're tightly spaced, so that indicates a strong electric field. Whereas if you're way out here in this area, the electric field lines are actually quite far apart, and that indicates a relative weakness in field. It's not a quantitative thing, it's a qualitative thing, but you can definitely tell at a quick glance where the field is stronger or weaker. And of course, we've already talked about this, that it's defined by convention and by history and mathematically to be the direction. The field lines indicate the direction that positive charges will feel a force. You don't have to draw separate pictures for negative charges because they'll just go the opposite direction from the arrow, right? So here are some pictures. The blue lines are electric fields for a few common configuration of charges. So in the upper left here, this would be what chemistry teachers might call a dipole moment, or an induced charge separation, or just two neighboring equal but opposite charges. So we're considering both the negative and positive to be the sources of the electric field. And so you would formally calculate what this electric field is by calculating Coulomb's law at every single point in space, dividing out the second Q, and determining the strength and direction. But if you just use these rules that I just went over, right, and you know that the field lines need to be coming out of the positive charge, and of course, if you're very close to the positive charge, that's all you will feel is electric field from the positive charge. So they start off looking just like this picture back here, right, just coming out radially. And likewise, if you're very close to the negative charge, you will see them coming in more or less radially. And it's only as you get a little bit further away from one charge where you have to actually get a significant contribution from the other charge, they will bend and warp to get out of that radial alignment. And if you just sort of do what intuitively the rules tell you, they can't cross, right? And the number of field lines also would be proportional to the amount of charge. So if these are equal and opposite charges, you need to draw the same number of field lines coming out of the positive as you do into the negative. Then you can just basically kind of draw this picture qualitatively. Likewise, if you had two positive charges side by side, you would get a picture like this. Since the field lines can't cross, but they need to be coming away from both positive charges, right? This is how they'll distort. And indeed, if you were to do Coulomb's law exactly in the middle, you would get no net electric field there because the force contributions would be equal and opposite. A point positive charge near a line of negative charges will do this. And if you have a series of positive charges and then a concentration of positive charges in one place, you will get stronger field lines there, right? As you get far away from the surface, though, what do? You just recover these straight lines as if you only had a straight surface there, right? So that's a useful trick to use when you're drawing these pictures, is to think about what does the charge distribution look like if you get really, really far away. So for instance, in this upper right-hand picture, you have two positive charges separated by some small distance. If you're close to these positive charges, then it really does matter that the positive charges aren't right on top of each other, right? You have this distortion in the field lines. But if you get really far away, like get 5 miles away from these two positive charges, how would you tell the difference between those two slightly separated single Coulomb charges and one big 2 Coulomb charge right in the middle? There shouldn't be a difference if you get really far away. And if you start thinking about what these field lines will do as you get farther and farther away, they'll tend to go to being just radially, looking like they're coming radially out of the center here. Okay, and on this picture, if you get really far away, what will happen is you won't see any field lines at all, because all of these field lines that are coming away from this positive will eventually circle back and come back into this negative charge. See, that field line right here is going to connect to this field line outside of the picture somewhere. And of course, that is what's happening with every neutral atom in the universe, right? If you get inside that atom, there's all these intense electric fields between the charges contained within. But since the atom is overall neutral, if you get outside of there, some significant distance away from the atom, a couple atomic diameters away, it's as if there's no charge there at all, because the electric field lines are all contained within. So if you actually have to calculate, the electric field due to a whole bunch of charges in your area, a whole bunch of source charges, what you do is just the same thing you would do with Coulomb's law. You would find the electric field from the first source charge and then do a vector addition with the electric field from the second source charge and just do a vector sum of them all, right? And then you would get the net electric field at that point. And that is the electric field that a charge would feel if it gets dropped in, right? A little bit of terminology here is the charges that you're thinking about setting up the field are called the source charges. So every single charge in these pictures would be the source charge, because they're the source of the electric field. And whatever charge you would drop into the field that would then respond to it, if it was a negative charge, it would kind of swim upstream this way. And if it was a positive charge, it would get pushed along the field. Those are considered the test charges, right? So source charges sourcing the fields, and test charges being the ones you put in the fields to see what happens. Okay, that's a good place to stop for today.